Swayam Prabha. Digital India. Educated India.
Hello friends, welcome to this lecture series of BSc with Chemistry, discipline specific elective of quantum chemistry, spectroscopy and photochemistry. In this lecture, we will discuss photochemistry. So friends, let us once again revise about the electromagnetic radiation. During our discussion in electronic spectroscopy, we have already seen about the electromagnetic spectrum. Basically, what are electromagnetic waves? These electromagnetic waves are very much similar to ocean waves that we already have seen, that they transmit energy in the form of wave, just like ocean wave, and they are produced due to the vibrations of charged particles, and in addition to that, they are composed of electrical and magnetic waves. We also know that some of the electromagnetic wavelengths are very large and some of them are very short. And as we go on increasing the frequency from radio waves, the wavelength of this electromagnetic radiation goes on decreasing till the gamma rays, and the energy increases very significantly. This point also we have discussed that presently in your room, along with the visible range wavelength of the electromagnetic spectrum, you have radio waves, microwaves, and actually there is a chaos of waves across the room right now present in front of your eyes. In general, if you could see all of them, probably you could have seen nothing. And therefore, the nature has given us a gift to tune our eyes only to the specific region of electromagnetic radiation, that is between say around 400 to 700 nanometers, so that we can watch our TV very comfortably, or we can watch this beautiful nature. Basically, the objects appear colored because this electromagnetic radiation, it interacts with the matter, wherein some of the wavelengths are absorbed and some of them are reflected. And now our eyes can tell us only about the specific part of this electromagnetic wave interaction with matter, and that too which we can particularly see. However, our eyes cannot tell us what happens to UV rays, IR rays, or the electromagnetic radiation in microwave region. Now, everything around us emits, reflects, and absorbs the electromagnetic waves based on their nature. And the electromagnetic waves interaction with matter gives a signature pattern. And due to their common composition, we can actually interpret about their structure and their behavior based on their interaction with the electromagnetic radiation. Correct? This particularly we have seen in electronic spectroscopy. We can also determine the patterns and trends of their behavior as well. This is all we have seen during our previous lectures of molecular spectroscopy. Moreover, in this particular lecture, we will see the effect of absorption of light radiation to carry out chemical reactions. And this is particularly known as photochemistry. Particularly, molecules, when absorb light, the bonding molecular orbital electrons, they shifts to anti-bonding molecular orbitals. And they actually get more effectiveness in carrying out the chemical reaction because now they are in the higher energy state. And therefore, in a photochemical reactions, usually a particular atom or a molecule which we can excite to a higher energy level, say instantaneously, and this is particularly not possible in thermal reactions, isn't it? And therefore, this technique is very useful application in studying all such photochemical reactions. In atmosphere, many essential photochemical reactions are taking place based on this particular principle. And on account of these photochemical reactions, nature maintains the balance of heat and sustainable environment for the living beings on this earth. Say for example, the formation of ozone from oxygen in the Earth stratosphere. Apart from chemistry, the photobiology is equally important to study these aspects in the nature. And there are numerous number of examples in and around us happening due to photochemical interactions. Let us try to understand how the photochemical reactions are different than these thermochemical reactions. So, say this interaction of this electromagnetic radiation with matter many a times results into a physical change, or many a times it results into chemical reactions whose rates and mechanisms are studied after the initiation of the radiant energy, or say initiation by the radiant energy. And this particular study is known as photochemistry. Although the term radiation includes all the type of electromagnetic waves, right from say low frequency microwaves to high frequency X-rays and gamma rays, etc. This radiation of photochemical importance are those which basically lies in the visible or ultraviolet region, say for example 8000 to around 2000 angstrom, or say 800 to 200 nanometers. And the reaction which takes place by the absorption of light by the reacting substances are called as photochemical reactions. So these reactions are generally brought about by the absorption of light radiations of say visible or ultraviolet region. And in all such cases, the light energy is absorbed, is basically stored in the substance, and then it is used for the bringing about the reaction. There are many examples, say large number of different types of reactions can be brought about by the exposure of suitable lights with the substances. And there can be many examples. So two well-known examples of the photochemical reactions are photosynthesis and the formation of HCl from H2 and Cl2, which is otherwise not possible. Apart from that, if we particularly try to differentiate the photochemical reaction, basically that takes place when the incident photon has sufficient energy so that it can result in the excitation of one of the reactant from the ground state to excited electronic state. And apart from that, say we'll see where basically the difference of photochemical reactions or thermochemical reaction is. These photochemical reactions, they differ from the ordinary chemical reactions because they occur by absorption of heat energy, and it can take place in absence of light. And such reactions are usually called as direct reaction or thermal reaction, isn't it? Say for example, we can see here the differentiation of thermochemical reaction and photochemical reaction. So thermochemical reactions, they involve absorption of heat, whereas the photochemical reaction, they involve the absorption of light. These thermochemical reactions can take place even in dark, and photochemical reaction take place in the presence of light. This thermochemical reaction is markedly affected by temperature, whereas this photochemical reaction has a negligible effect of temperature. Like in case of thermochemical reaction, the reaction involves decrease in free energy, that is delta G is negative. In case of photochemical reaction, free energy of reaction may increase or decrease depending on what is the reaction. So delta G can be positive or negative. Say apart from that, the activation energy arises from the intermolecular collisions, or it is supplied in the form of heat in case of thermochemical reaction. Whereas in case of photochemical reaction, the activation energy is acquired by the absorption of photon of suitable energy. The very suitable example for thermochemical nature of the reaction is formation of ammonia, and very familiar example for this photochemical reaction, as we have seen, either you can take example of photosynthesis in plant, and or this example, that is H2 plus Cl2 on absorption of light is giving twice HCl. So friends, whenever a substance or a molecule, it absorbs light energy, and the molecule which is particularly in the ground state, electronic state, it goes to excited electronic state. And once it goes to excited electronic state, it can release its energy in several forms. And various phenomena due to the release of this energy or the shifting of this higher electronic state to lower electronic state, it is very well explained by this Jablonski diagram. So we will see here in detail this Jablonski diagram. This particular diagram we have already seen in while our discussion in electronic spectroscopy. We have seen this diagram during the discussion of Frank-Condon principle. However, let us try to understand one of the additional phenomena over here. Say in this particular Jablonski diagram, as already seen, this light absorbed by the system is used up in bringing up a photochemical reaction. But the absorbed light may not necessarily bring about a photochemical reaction. Moreover, it may give various other phenomena as well. And the various phenomena they are shown by the excited molecules, and these molecules from the excited state, when they come to ground state or subsequent lower energy state, various phenomena occur. Let us understand one by one. So after excitation, the molecule returns back to the ground state, and while returning, there can be several returning mechanism. So these transitions, basically, you can see over here. So these transitions, they can be predictive of like non-radiative transitions, radiative transitions, and one of the additions that we have shown over here, apart from that we have shown in electronic spectra, is one which is chemical reaction. So let us see one by one. So in non-radiative transitions, what we see, these kind of transitions are those transitions which do not lead to emission of light radiation, and they are called as non-radiative transitions. So basically, these non-radiative transitions, they can be of two types. You can see over here, internal conversion, which takes place at this time rate, and internal crossing systems. So this is ISC, intercrossing systems. So this is the other phenomena, that both of the states or both of the transitions, they are non-radiative. So this what we can say is, if the molecule loses some of its energy in the form of heat, and the higher singlet state shifts to lower singlet state, that is say from S3 to S2 or S2 to S1, it is called as internal conversion. And this process occurs within very less time of say 10 to the power minus 11 seconds or so. And since the energy is released in the form of heat, it is non-radiative or radiation-less transition, we can say. Apart from that, if the energy released in the form of a heat and the molecule changes its spin state or say spin multiplicity, if it changes, then such processes are called as inter-system crossing. They are called as inter-system crossing. And say particularly in this case, the molecule comes from S2 to T2 or S1 to T1 and so on, likewise. So these transitions are spectroscopically forbidden, and they actually occur at very slow rates. Apart from these non-radiative transitions, there can be radiative transitions, you can see here. Okay, fluorescence and phosphorescence. So what are these radiative transitions? So these radiative transitions are the transitions which lead to the emission of light radiation, and they can be of two types, like the fluorescence and phosphorescence. So what is fluorescence? So if a molecule comes to ground state from the first excited singlet state, from this to this, say from S1 to S0, it leads to emission of radiation, and we call it as fluorescence. And this transition is spectroscopically allowed, and it occurs in about say 10 to the power minus 9 to minus 7 seconds or something like that, isn't it? Apart from that, the other phenomena is, if the molecule comes from the comes to ground state from the first excited triplet state, you can see over here. This transition is basically spectroscopically forbidden, but such transitions are known as phosphorescence, or the light which emits in this process is basically known as the phosphorescence. And this process is relatively slower, and it usually occurs in say around 10 to the power minus 3, or up to, it goes up to 10 to the power 2 seconds, and therefore many a times we call it as a delayed fluorescence. both the fluorescence as well as phosphorescence occur at low frequency compared to the excitation frequency, because some energy is lost in the form of heat in non-radiative transitions. Apart from these two, there is a third possibility of chemical reactions or chemical transitions. So now what are these? In some cases, if suppose none of the transitions like fluorescence, neither fluorescence nor phosphorescence takes place after the excitation, then what happens with the molecule? So basically the molecule undergoes a chemical reaction, and whenever molecule undergoes a chemical reaction, it is called as the photochemical reaction. And since the singlet state returns quickly back to the ground state, the probability of photochemical reaction is more in triplet state, which is comparatively a slower state, isn't it? And therefore most of the photochemical reaction, they occur through the triplet excited state and not the singlet excited state, isn't it? So you can see over here this particular part of chemical reaction. This is very important, and this leads to one of the important aspect of chemiluminescence that we are going to see in this photochemical reaction part or photochemistry part. So in luminescence spectroscopy, basically what do we study? We study fluorescence, we study phosphorescence, and we study chemiluminescence. Although we have seen the fluorescence and phosphorescence in electron spectroscopy in detail, let us overlook once again this particular aspect. So what is fluorescence? So when a beam of radiation is incident on a certain substance, they emit visible radiation instantaneously, and this phenomena is actually called as fluorescence. So it is observed basically due to the molecular transition, say, from the first singlet excited state to the ground state. And this phenomena particularly shows several properties, interesting properties, that this is actually the instantaneous phenomena and starts immediately after the absorption of light. Likewise, we have already seen that the different substances of fluorescence light they emit with a different wavelength. The extent of fluorescence depends upon the nature of solvent and the presence of certain anions in the solution. It is also, we also know that it is exhibited by liquid as well as solid. And also we know about fluorescence that as soon as the incident radiation is cut off, the fluorescence is stopped. You no more you can see it, because it is a instantaneous phenomena. Examples also are very familiar to us. That is a solution of chlorophyll, which shows a red color fluorescence when it is illuminated with in presence of light. Apart from that, there are various examples that we have already seen. We have also seen the application of fluorescence in the different type of the defect of the forged document. uh, I mean, detection of the inks which are used in the forged document, or you can use it in particularly what we have seen earlier also, that the ringworm may be detected using the fluorescence which is caused by the UV radiation. This fluorescence of the phosphorus is being used in the fluorescence lamp. There are many examples. Likewise, fluorescence also, very shortly we will see that when a beam of light radiation is incident on a certain substance and they emit light continuously even after the incident light is cut off. So such kind of phenomena is basically known as delayed fluorescence or phosphorescence. You can see over here. See, even after light is cut off, I mean, you go on continuing the image which is present over here. This is just like this particular image. So the substance exhibiting the phenomena are called as the phosphorescent substances. Again, this phenomena occurs when the transition takes place from the first excited triplet state to ground state, isn't it? And this particular phenomena, phosphorescence, has got particular typical properties. This particular phenomena is caused chiefly by the ultraviolet and violet radiations. This phenomena is mainly shown by solids. The magnetic and dielectric properties of the say phosphorescent substances are different before and after the illumination, and therefore this is actually due to the change in spin of the electron and so on. We have already seen all these properties. There can be several examples of phosphorescence, like sulfide of zinc, alkali and alkaline earth metal exhibit the phenomena. Many dyes, when fixed by the suitable methods, show phosphorescence. The minerals ruby, emerald show phosphorescence. We can use this phosphorescence phenomena in many of the places. like luminescent paint, they actually contain about 2 to 5% of alkali chloride and a trace of heavy metal sulfide. Such a mixture is generally used in painting, uh, wristwatch dials or watch dials, electric switches, road signals, etc. The most important is chemiluminescence. Now, many a times what happens, instead of returning to the ground state back from the either singlet excited state or the triplet excited state, the certain chemical reaction results in the formation of products which are in electronically excited states. So when these excited molecules return to the ground state, they emit extra energy in the form of visible light radiation. And such phenomena of emission of visible light through a chemical reaction is known as chemiluminescence. So what we will do, we will see what are the other important aspects of chemiluminescence. So chemiluminescence is, as we have seen, it is defined as the production of light by the chemical reaction, and it is actually the reverse of photochemical reaction, isn't it? So the basic condition for substance to be chemiluminescent is that it should raise the sufficient energy to raise at least one of the reactant to electronically excited state, so that when it returns to the ground state, it emits light. Say for example, the glow of phosphorus and its oxide, uh, or you can see the oxidation reduction reaction of the hydrazine, isn't it? Or you can see the cold light emission by glowworms or fireflies. This is very interesting phenomena in nature. This is an example of bioluminescence reaction, which involves the oxidation of luciferol, which is actually a protein, by atmospheric oxygen in the catalytic presence of the enzyme, which is called as luciferase, isn't it? The other interesting aspect is the reaction between alkaline solution of say hydrogen peroxide and chlorine, or say hypochlorite ion, which produces a red glow at number of wavelengths. The other example is electron transfer reactions. Also, they are carried out on this principle. Apart from that, the aromatic anions and cations interactions generated during the electrocatalysis, or sorry, electrolysis of the large polycyclic hydrocarbons, they also give the chemiluminescence. Apart from that, the luminescence which we observed at night in the ocean by due to the jellyfish, it is actually said that it is due to the decay of the luminous jellyfish. This particular jellyfish luminous light in the ocean you can observe, particularly in the night time, isn't it? So these are particular properties of the chemiluminescence. So now let us see what are the laws governing the absorption of light. Means what happens when the light is absorbed by the molecule. So there are particularly two laws. So when a monochromatic light, or say light consisting of a single wavelength, is passed through a medium, what happens? Some light is absorbed by the medium, while a part of the incident light is reflected and remaining part is transmitted. However, it is only the part of light absorbed by the medium that can bring about the chemical reaction, and the part which has been reflected is of no use, isn't it? And therefore, the amount of light absorbed is governed by two laws, and these two important laws are Lamberts law and Beer's law. So what are these two laws? We are going to see these two laws in detail. So say in case of Lamberts law first, we know that what Lamberts law says, it says when a beam of monochromatic light is allowed to pass through a homogeneous medium, the decrease in the intensity of light with the thickness of medium is directly proportional to the intensity of incident light, isn't it? Whereas the second law, Beer's law, which is actually known as Lamberts-Beer's law, we can say that it is the improved version of the Lamberts law. What does it say? It says when a monochromatic beam of light passes through a homogeneous solution, the decrease in the intensity of light with the thickness of solution is directly proportional not only to the intensity of incident light but also to the concentration of solution. That means there is the additional part of concentration has already come into this particular law, and therefore this particular law is also known as Lamberts-Beer's law, isn't it? Let us see what are these laws and what are their mathematical implications. So in case of Lambert's law, it was given in 1760 around. So what this law is, we have already seen that when a beam of monochromatic light is allowed to pass through a homogeneous medium, the decrease in the intensity of light with the thickness of medium is directly proportional to the intensity of incident light. This we have seen just now. This is what we can say is the statement of the Lambert's law, which means that this particularly I can write down from this particular statement that di by dx is proportional to this particular intensity, and your negative sign to particularly this equation indicates the decrease in intensity with the thickness, correct? Whatever is the thickness of your cell. So it can be further represented as minus di upon dx is equal to k into I. Say let us just for the sake of understanding call it as 1. Okay, now this k is proportionality constant and it is also called as the absorption coefficient. So I can write down this particular equation in this form, isn't it? So I can write down like minus di upon I is equal to k into dx. So if I integrate this particular equation, say within the limits of say at x is equal to 0, I is equal to I0, that is original intensity, and say at x is equal to x, I is equal to I. So if I integrate within this limit I0 to I, say from 0 to x, what I get this particular expression, that is minus ln I upon I0 is equal to k into x. So I can write down in another way, that is I upon I0 is equal to e to the power minus kx, or I is equal to I0 into e to the power minus kx. This is known as Lambert's law. Is it? Similarly, we can see in case of Beer's law or Lambert's-Beer's law in combination, since now this intensity of the incident light, it is dependent on the concentration of the solution along with the thickness. So both the part has to come into it. So both the part have taken part into here. So my original expression will now be of this form, that is di upon dx minus of di upon dx will be proportional to I as well as c, isn't it? And therefore this can be written in this form, that is minus di upon dx is equal to alpha into ic, where this alpha is the proportionality constant now, and it is called as molar absorption coefficient, and actually its value depends upon the nature of absorbing solute and the wavelength of the light which is used. Obviously the c is the molar concentration of the solution of particular solution that we have taken under study. I can write down from this equation number 3, I can write down that minus di upon I is equal to alpha into c into dx. If I integrate it within the limit of say at x is equal to 0, I is I0, that is the original intensity of the light, and at x is equal to x, it is I is equal to I, whatever light has been absorbed and whatever has been reflected, that we have noted. So this I upon I0 within the limit of I upon I0 to I, if we integrate di upon I, and within the limit 0 to x, if we integrate alpha into c into dx, I get this particular expression, and therefore I can write down I upon I0 is equal to e to the power minus alpha into cx, or say I is equal to I0 into e to the power minus alpha into c into x. This particular equation 4 is known as Lambert's-Beer's law, is it? So the Lambert's-Beer's law equation, it can further be written as in this form, because I can always write it down in the form of from natural log to the log to the base 10. I can write down minus 2.303 into log I upon I0 is equal to alpha into c into x. So if I further solve it, I get this particular expression, and finally I can write down I is equal to I0 into 10 to the power minus epsilon c into x, where this epsilon is nothing but molar extinction coefficient, which is nothing but alpha upon 2.303 factor, isn't it? And this is many a times this is known as molar absorptivity. Okay, it has got very interesting implications. So that means my absorbance is equal to log of I upon I0, and therefore my absorbance is equal to epsilon into c into x, is very interesting expression for my Beer's law, and it is very useful in the sense that if the concentration of solution is 1 molar and the thickness of medium is of 1 centimeter, in that case my A will become epsilon, and therefore the molar extinction coefficient can be defined as the absorbance produced by 1 molar solution when placed in the cell of thickness of 1 centimeter, isn't it? So that is what is the implication of this molar extinction coefficient. We can solve many numerical based on it, and this particular example is very useful in laboratory purposes. So I can find out, say for example, the molar extinction coefficient of a substance if it is given as 14,000 at lambda max, at its lambda max. So with a cell of 1 centimeter thickness, the observed absorbance is say 0.85. So what is the concentration of the solution? So I want to find it out. So I can use this equation, A is equal to epsilon into Cx. So I can find out what is the concentration, A upon epsilon into x. If I substitute, I can find out that it is 6.07 into 10 to the power minus 5 molar solution. So likewise, I can find out any parameter if I know the absorbance, I can find out concentration. If I know the concentration, I can find out the absorbance. Likewise, I can follow this particular law. See, apart from the numerous benefits of the Beer's-Lamberts law, there are many limitations to this Beer's-Lamberts law. What are those limitations? One by one we have written over here. This law is not obeyed if the radiation is not monochromatic. So we need a single beam monochromatic source of light. Apart from that, this law gives valid results when used for dilute solutions only, since in concentration solution the linear relationship between the absorbance and concentration is not valid, and at higher concentration there are distinct deviation from the linearity. You can see over here as the concentration go on increasing. So this particularly is the expected line. However, it goes like this. So there occurs a deviation. So at higher concentration, the refractive index also changes, and therefore this is not valid. And apart from that, the temperature also need not vary to a great extent, since that leads to the bathochromic effect of ions in solution. That is, the absorption band shift towards the longer wavelength. These are the limitations to the Beer's-Lamberts law. So after absorbing the energy by the molecule at the excited state, the molecule leads to the photochemical reaction or chemical reaction, and such a chemical reaction comes under the category of photochemistry. So whenever this happens, there can be two possibilities. So there are basically two laws of photochemistry, and these two laws are known as, the first one is known as Grothus-Draper law of photochemical activation, and the other one is Stark-Einstein law of photochemical equivalence, which is actually known as quantum activation. We'll see one by one both of them. So in case of, say, Grothus-Draper law, this particular law is also called as actually the first law of photochemistry or the principle of photochemical activation. It was actually put forward by the Grothus theoretically in 1818, and later on it was confirmed experimentally in 1839 by Draper. It states, actually the statement of this particular law goes like, it is only the absorbed light which is effective in bringing about a chemical reaction. What does it mean? It means that the transmitted or reflected light does not cause any chemical reaction. That means it goes away. And the second law is the Stark-Einstein law of photochemical equivalence. What does this law says? This law says that basically it says that each atom or molecule of the reacting substance that takes part in the photochemical reaction absorb one quantum of radiation, that is photon, to undergo the chemical reaction, isn't it? So this law is actually called as the second law of photochemistry, or principle of quantum activation, isn't it? It was put forward by Stark in 1908 and by Einstein in 1912. In both of them, they worked independently. This law states that each atom or molecule of the reacting substance that take part in the photochemical reaction absorbs one quantum of radiation to undergo the reaction. Say if nu is the frequency of the absorbed radiation, then the energy of quantum radiation is given by, say, h nu or hc upon lambda. This we all know, which corresponds to the energy absorbed by one atom or one molecule according to Stark-Einstein's law. So the 1 mole of substance contains the Avogadro equivalent molecules, and hence the energy absorbed by 1 mole is given by this particular equation number 6, that is E is equal to n into hc upon lambda. And this energy absorbed by 1 mole of reacting molecule or energy absorbed by 1 mole of photon is called as 1 Einstein. This is particularly the new unit used in photochemistry particularly. Quantum yield or quantum efficiency is one of the important aspects in photochemistry. So according to Stark-Einstein law, one molecule should react with each of the quantum or the energy absorbed. However, it is not the case with all the reactions. The number of molecules reacting per quantum of energy which is absorbed is called as the quantum yield or the quantum efficiency of the reaction. It is usually denoted by phi, and it can also be defined as the number of moles reacting per Einstein of the energy absorbed here, as it can be shown over here. So if the Stark-Einstein law is strictly obeyed, then the quantum yield of the reaction should be equal to 1. This is quite obvious, isn't it? So however, but what is in practice? For many reaction, it is either greater or less than 1. There are several examples. Some of the examples are shown in the table over here. If you if you see this particular reaction, there is quantum yield is 2. For this reaction, it is 2. For this reaction, you can see that is one of the very important photochemical reaction of formation of this hydrochloride from hydrogen and chlorine after the absorption of light radiation. It gives 10 to the power 5. Then for this reaction, it is 10 to the power 3. Likewise, there are certain reactions for which the quantum yield is very low, say up to 0.01 or maybe lower than that. So on what basis actually this is decided? This is decided on the basis of this particular actually formula. So in order to explain such variations, it was suggested that the photochemical reaction involved two distinct stages. So what are these two distinct stages? Namely, the primary processes and the secondary processes. So in primary process, the quantum of energy absorbed to form the excited molecule are important. These processes basically, or these primary processes, they are totally dependent on the absorption of quanta of energy from the radiation. And hence, the law of photochemical equivalence can be applied to these processes. So you can see this process. Okay. Apart from that, the secondary processes are like in secondary process, these excited molecules may undergo various changes leading to high or low quantum yield, and these processes have nothing to do with the absorption of radiation, and hence they are independent of light. So both the type of reactions are there, and accordingly the quantum yield actually varies. We will see how these quantum yield vary depending on these processes. So what are the conditions for quantum yield equivalent to 1, ideal conditions? Or what are the conditions for high yield or low yield, that we are going to see over here. So in order that the law is followed very rigidly, that is to have a quantum yield 1, these particular conditions are necessary to be followed. What are these conditions? These conditions are, say, all the molecules of reacting substance should be at the same energy level and all should be equally reactive. This is one of the important conditions. If this is so, your quantum yield will be equivalent to 1. The second condition is if the reactivity or the velocity of the reaction should be independent of the temperature, except that the change in temperature is effective in increasing the absorbing capacity of the system. And the third one is the product of absorption must become unstable with respect to the original system. Then and then only my quantum yield will be equivalent to 1. Otherwise, it will be higher or lower. So what are the reasons for high quantum yield? So these are some of the points which we have tried to point out over here. So what are the reasons for high quantum yield? Say the atom or free radical produced in the primary process may start a series of chain reactions. And in all such cases, the quantum yield depend upon the extent of the chain reaction, that is, how far the chain reaction proceed before the termination of the chain. Moreover, an intermediate product can also be formed, or it may be formed, which act as a catalyst, making the further reaction feasible without the absorption of radiation. The other point is the reaction involved may be exothermic, hence heat evolved may activate the other molecules, thereby causing them to react without the absorption of additional quanta of radiation, and therefore your quantum yield may actually escalate up. Apart from that, the collision of activated molecules with the other molecules may result in the transfer of some of their energy, so that more molecules may be activated. This is one of the important aspects to be considered, and the reaction may gain the higher quantum yield. You can see these are the examples that already we have seen in the previous table, isn't it? In all such cases, you can see the quantum yield are very high than the expected value from the formula, because of any one of the reason which we have discussed. Apart from that, there can be several reasons for the low quantum yield. Say the excited molecules may get deactivated before they form products. This can happen. This may happen due to the collision of excited molecule with non-excited molecule, or with the walls of the vessel, which may cause them to lose their energy and get deactivated. Apart from that, the primary process may get reversed. This is also one of the aspect that may take place. Apart from that, the fragments obtained by the dissociation may recombine to form the original non-excited molecules, and therefore it may return back to their original state. In that case also, the quantum yield will decrease. Apart from that, the other reasons can be the all absorbing molecules may not receive enough energy to enable them to react, because part of the absorbed energy may be lost in the form of fluorescence before they actually could react. And therefore, in this case also, the quantum yield may come lower. One of the additional reason can be molecules with which activated molecules are to react may have energy below average, so that even in spite of receiving energy from the activated molecule, they may not reach to the point of reaction. And therefore, this is one particular example, isn't it? You can see over here the quantum yield. It is very low in both the reaction from this malic acid to fumaric acid. You can see the quantum yield, and any one of the reaction it may take place. And therefore, for this photochemical reaction or photochemistry is one of the important tool in understanding all these aspects. So friends, in order to determine the quantum yield of a photochemical reaction, the two important parameters are to be determined using the experiments. These parameters are, number one, the number of moles of substance that reacts in a given time. This we need to know. And the second is the number of Einsteins of radiations absorbed by the same substance in same time. If these two parameters are known, we can calculate the quantum yield. So for this, the experimental setup is actually given over here. It involves the light source. You can see over here The source of light. The light source may be a sunlight or an arc lamp or mercury vapor lamp or the discharge tube or the tungsten lamp, or it can be any other source of light. So the mercury vapor lamp is usually the best source of ultraviolet radiation, while the tungsten lamp is used for the visible region. So this we all know. Then we need a monochromator, because if your light is not monochromatic, single beam, if it is not a single beam finely focused, then we may not get actually the required results. So monochromator is required. What is the function of monochromator? The function of monochromator is that it is used to isolate the desired wavelength, and this makes the calculation of energy possible. Usually a color filter is sufficient for this particular purpose. Then we need a reaction cell. So the reaction cell is generally made up of glass or a quartz with optically plane windows. And for visible light, the reaction cell and the other parts of instruments are generally made up of glass. And for ultraviolet light, all the optical parts are made up of quartz. This we all know, because the glass absorbs ultraviolet light. For solution of reaction cell, actually we use many a times we use the quartz cell particularly. And apart from that, we need to provide particularly stirrer over there, so that uniformity or homogeneous mixture should be maintained. And it actually varies depending on the design of the particular apparatus, isn't it? And the cell size also varies from reaction to reaction. Apart from that, what is important is the detector. So what is the function of detector? Function of detector is to determine the intensity of light which is coming from the reaction cell, and the intensity is measured first with the empty cell and then with the reaction mixture, so that we can compare what is the before and after energy sense. So the difference between these two readings, that is before and after, will give the amount of energy absorbed. And particularly to detect this particular intensity difference, we can use several detectors. Say you can use radio micrometers, photoelectric cells, thermopiles, chemical actinometers, and so on. So actinometry. What is actinometry? This is relatively a new term. Say a chemical actinometer method, or say chemical actinometer system or physical actinometer, they are actually one and the same thing. Or a chemical system or a physical device that determines the number of Einsteins absorbed is actually known as actinometer. Although it is not very accurate, but it is a convenient method for measuring the number of Einsteins absorbed. So in this device, a standard photochemical reaction is used to estimate the energy of the radiation absorbed. One of the actinometer which is very commonly used is the uranyl oxalate actinometer. What is this actinometer? It consists of say 0.05 molar oxalic acid mixed with the 0.01 molar uranyl sulfate solution. And this uranyl sulfate serves to sensitize the decomposition of oxalic acid on exposure of violet or ultraviolet light. You can see over here, isn't it? So the wavelength of the required light, which falls under the range of say usually 2540 Armstrong to 4350 Armstrong, and the extent of decomposition of oxalic acid is determined at the end of the experiment by its titration with the standard potassium permanganate solution. So it is a analytical titration. So the assumption made is that the amount of decomposition is proportional to the product of intensity of light of a given wavelength and the time of exposure, so that we can determine it, isn't it? And the apparatus is first basically standardized with respect to the radiation of the different wavelength, and it is therefore possible to calculate the amount of energy of light radiation of a given wavelength which is absorbed in case of the photochemical reaction. All these measurements are made before and after passing the light through the reaction cell. The decomposition of oxalic acid takes place actually in this fashion, isn't it? Where this uranyl ion is obtained from this uranyl sulfate, which is actually behaving as photosensitizer. So this is particularly behaving as photosensitizer. How we can proceed in this actinometry? So what we need to do first, we need to have the reaction cell which is kept empty, and then we allow the light to pass through it, and then we determine the intensity of this light through this blank cell, okay, through this empty cell. Then this cell is filled with the reaction mixture, and then we allow the light to pass through this filled reaction mixture for a known time. So the intensity of light after passing through the reaction mixture is measured, and the difference in two intensities before and after will give you the amount of energy absorbed by the reaction system. Apart from that, the number of moles reacting in the same time can also be determined by the suitable analytical technique by finding, say, the initial and the final concentration of the reaction mixture, which can be a very easier task. So from the value of number of moles reacted and the number of Einsteins absorbed, we can actually calculate the quantum yield, isn't it? One of the diagrammatic sketch has been tried over here. In practice, actually, you can use the static batch mode, or you can use the flowing gas mode. So in batch mode, what we do, we during measurement, this actinometer is exposed to radiation for a fixed time, and then the actinometer is closed again and analyzed for the change in the reaction mixture composition. This can be done in this batch mode. Whereas in continuous flowing gas mode, the exposure to solar radiation of actinometer gas is usually enabled, and after passing of gas through the illuminated reactor in the given time, its composition is analyzed using a suitable detector. We can have the actual experience of the experimental part. If you go through this numerical, you can be sure that how it is very easier. So if you try to solve these numericals of, say, particularly the radiation of wavelength of 2500 Angstrom was passed through the cell containing 10 ml of solution, which was 0.05 molar in oxalic acid and 0.101 molar in uranyl sulfate. So after absorption of 80 joule of radiation energy, the concentration of oxalic acid was reduced to 0.04 molar. So initially it was 0.05 molar. So in this case, we need to calculate the quantum yield of photochemical decomposition of oxalic acid at a given wavelength. If I try to use this formula, E is equal to N into Hc upon lambda, I can substitute the value of this Avogadro number, then Planck's constant, and the speed of light upon the lambda. Wavelength is given. So my energy is this. So the radiation energy absorbed is 80 joules. So number of Einstein absorbed will be this much. So now the decrease in concentration of oxalic acid is 0.01 molar actually, and therefore the quantity of oxalic acid decomposed in 10 ml of solution is 0.01 into 10 upon 1000, that is 1 into 10 to the power minus 4 moles, and therefore the phi actually quantum yield is 0.599, which can be calculated very easily. So this is one of the example how we can perform this in laboratory. Apart from that, there are many processes which can be studied based on this photochemical reactions. A very important aspect is covered in the photochemistry, that is the energy transfer processes, which includes the photosensitization and the quenching in this particular process. So there are basically many substances which do not react directly when exposed to light. This can happen actually. So however, if some third substance is added which is photochemically active and which helps in starting the photochemical reaction, then this third substance is actually called as the photosensitizer. Actually, this third substance, it may not undergo, or it usually does not undergo chemical change. It merely absorbs the light energy and then it transfers the absorbed energy onto the reactant, so that the photochemical reaction start, isn't it? And whenever such process start, it is known as photosensitization, and the substance which actually transfers the energy on absorbing it to the reactant is actually known as the photosensitizer, isn't it? But you can actually say that this photosensitizer simply can act as the carrier of energy. So it is a carrier of energy. So in order to understand this sensitization phenomena, we can take very simple example. You can see this usually general example. So this is a general donor acceptor mechanism. Okay. In this mechanism, only the donor, which is represented by D, is called as sensitizer. Okay. You can see at this figure even. So it actually absorbs the incident photon, and the triplet state of the donor is actually higher in energy than the triplet state of the acceptor. Okay. What I mean by this is triplet state of the donor. Okay, this is triplet state of the donor, and this is triplet state of the acceptor. So usually the triplet state of the donor A has to be higher, and triplet state of the donor has to be lower in energy. This is one of the primary condition for photosensitization. So the absorption of photon when produces the singlet excited state of the donor, that is this, it actually transfers the energy via intersystem crossing, and which gives the triplet excited state of the donor, which is known as 3D. Is it? So this triplet excited state then collides with the acceptor, which is the reactant, which we call it as a 3A, and the ground state of the donor. So if this 3A state, it gives the desired product, the mechanism is called as photosensitization. If, however, the product of interest, it results from your donor state, then this particular A is called as quencher, and this process is known as quenching. Correct? So some of the very common examples we have tried to study it over here. So a very common example is photosynthesis. Carbon dioxide and water vapors, they are existing in air, we all know, but they do not react in presence of sunlight, we all know. However, equally good, we know that in green plants, the pigment chlorophyll, they act as the photosensitizer, and they transfers the light energy to these reactant molecules like this carbon dioxide and water, and thereby they produce the carbohydrate of food, isn't it? They the conversion of sugar. Okay, and therefore this photochemical reaction which takes place in nature is very useful, and this is one of the best example of photosensitization. Apart from that, there is another example. You can see hydrogen molecule do not dissociate when exposed to UV light, but when hydrogen gas is mixed with the mercury vapors, then the exposed actually mercury vapors, they give the excited mercury state, and this particular mercury is acting as photosensitizer, and when it is exposed to UV light, the hydrogen molecule dissociates to give the hydrogen atoms through the particular reaction. Apart from that, you can have this particular example of actinometry, oxalic acid which undergoes decomposition in presence of uranyl sulfate, that we have already seen, which remains unchanged at the end of reaction, and these uranyl ions, they act as a photosensitizer in the reaction state. So these are very interesting aspects of the photosensitization, and very important phenomena of photosensitization can be explained based on this particular part. One of the important aspect is quenching, that we are going to see in a moment, but then the photosensitization leads to very vital reaction, and it leads to a new subject in photochemistry or photochemical reactions, which is usually known as photobiology, in which we can see the photosensitized reaction in nature. So the James Franck and Gustav Hertz, they received the Nobel Prize in 1925 in physics for their work in atom electron collision, for determining particularly this kind of mechanisms. So based on these lines, we can also understand the phenomena of quenching of fluorescence. In this case, you can see basically in this particular figure, you can see this fluorescence is quenched when the excited state species they undergo collision with the normal molecule before it has the chance to fluoresce, isn't it? So the usual phenomena of fluorescence is from ground state to singlet excited state, and then while transmitting energy back, transmitting energy, it gives the fluorescence and it comes back to ground state energy level. However, before coming to it, it collides with the molecule. It collides with some other molecules, and therefore the phenomena of quenching of fluorescence takes place. So before it fluoresces, this particular process takes place. So the quenching which is occurring due to the loss of energy from the excited state species to the colliding molecule is actually known as the quenching of fluorescence. So such kind of quenching can also occur when the molecule changes from the singlet excited state to the triplet excited state. This also is possibility. So while transferring from the singlet excited state, that is S2 to T2 or S1 to T1, while going so, this process may also take place during the transition. That is inter-system crossing transition also can lead to this particular kind of phenomena. So this particular phenomena is known as internal quenching. Internal quenching. So when your molecule is transferring energy from singlet excited state to triplet excited state, and if it collides, it is known as the internal quenching. Whereas if it is transferring, or if it is leading to fluorescence kind of phenomena, and while doing so it collides with the other particle, such kind of quenching is known as external quenching. So let us understand what this particular quenching is. Apart from this internal quenching, this quenching which is resulted in presence of externally added species like Q, where this Q actually takes up all the energy of this molecule, and then this particular molecule goes to some other state, that is Q dash, and the phenomena through which it occurs is known as external quenching, isn't it? And the mechanism is like this. See, whenever substance A absorbs energy, it gives the excited state, that is activation phenomena, and whenever while coming back to ground energy state, it releases energy, and this is in the form of fluorescence. Whereas instead of going to fluorescence, if it goes to internal system crossing, it is known as internal quenching. Whereas if it collides with this some external particle and it transfers the energy to some external particle, it is known as external quenching, isn't it? If you try to understand, or if you try to do some kinetics of this particular mechanism, and if you try to apply the steady state approximation to this concentration of this excited activated state of the reactant, I can actually find out the state, that is the intensity of light absorbed for this particularly A reactant. I can write down, if I apply the steady state approximation from the kinetics part. I have not gone into the details of the kinetics, but then if I apply the Bodenstein steady state approximation for this particular state, I can have this particular expression, isn't it? So, and if I say that this IF is the intensity of fluorescence, so the quantum yield of the fluorescence will be, that is phi F or phi Q will be IF upon IA, where IA is the intensity of the light absorbed and IF is the intensity of fluorescence. So if I go on doing with the kinetics, I can have this particular expression. So in absence of quenching, actually Q is equal to 0, and therefore my equation leads to phi 0, that is this. So phi 0 upon phi Q will give me this particular expression, and from this expression I can find out this particular expression. This is actually known as Stern-Volmer equation. If you see, this is the equation of a straight line, isn't it? And this Stern-Volmer constant, that is KSV, that is K3 into tau, actually the slope, and particularly you can find out the tau, which is the lifetime of this activated state of this your reactant. It will be given by 1 upon K1 plus K2. So from this particular Stern-Volmer equation, we see that this ratio of say phi 0 upon phi q is actually it depends on q, and which is apparent over here because it is equation of straight line, linear equation, y is equal to mx plus c, and therefore the slope is given by this k3 into tau, and from this particular slope we can calculate the value of tau, that is the lifetime of this particular activated state of your reactant. And this is what is very important aspect, and therefore when a pure chlorophyll solution is irradiated, this results in the fluorescence, and the addition of an external quencher such as oxygen or quinone, it quenches the fluorescence, and which can be studied using this particular process. So there are certain photochemical reactions which we can study based on our knowledge in photochemistry now. So let us consider this photochemical decomposition of HI. So this hydrogen iodide on photolysis will give hydrogen as hydrogen gas and the iodine. So the quantum yield of this particular reaction at say 207 to 282 nanometer is actually found to be 2. That is, this phi is equal to particularly 2. This suggests that the mechanism for this reaction involves two-step primary process, steps of primary process and secondary process. So what is primary process? So a molecule of HI absorbs one photon of light and dissociate to give the hydrogen atom and excited iodine atom. This is primary step, isn't it? Whereas the secondary step uh, is actually comprising of this particular mechanism. The product of primary process is used in this particular mechanism, and it follows this path, that out of all these reactions, if you see this H plus Hi will give you H2 plus I, and then this photochemically activated I will lead to this particular endothermic reaction, and other aspect, one of the possible reaction is these two hydrogen can give you hydrogen molecule. This is particularly the exothermic reaction. So if you see these reactions 1, 2, 3, 4 and 5, out of all these reactions, only reaction 1 and reaction 4, they are important. And so basically the important reactions, if you see, the only important part are these two because they are useful, and therefore if I try to add up the important reactions only, what we get this particular part, isn't it? So this particular part, this hydrogen iodide plus absorption of light will give me activated iodine, and then this reaction 1 and reaction 4. So in overall reaction will be this twice Hi will give H2 plus I2. So for every one quantum of light absorbed, two molecules of Hi are decomposed, and so the quantum yield of the reaction is 2, and therefore phi is equal to 2 is justified over here. Similarly, in case of photosynthesis of HBr, we see the hydrogen and bromine reacts in presence of radiation to form the hydrogen bromide. This we all know. Now this reaction, if you see, the quantum yield is very low, 0.01. Let us try to understand why it is very low. So this reaction has low quantum yield at room temperature, and as you go on increasing the temperature, this quantum yield increases. So this can be explained with the help of the mechanism. What this mechanism is particularly shown over here. The primary process is bromine molecule on absorption of energy will give you this particular part, that is bromine radicals, and in secondary process, the product of primary process then take part in the secondary process. You can see over here, is it? So out of these reactions 1, 2, 3 and 4, if you see, the reaction 1 is endothermic, and therefore it is very slow. If you look at reaction 2 and 3, they involve the reaction of hydrogen radical which are produced in reaction 1, isn't it? And hence their rates are also restricted by the reaction 1. So it is governed by this particular reaction. So the only important reaction is this fourth reaction, which is just the reverse of primary process. And as the primary process is reversed in secondary process, the quantum yield is very poor. And as you go on increasing the temperature, the rate of this primary process will go on increasing. And therefore, the quantum yield at higher temperature will increase. However, at lower temperature or at room temperature, this is going to stay very low. Similarly, if I try to see the photosynthesis of HCl, so hydrogen and chlorine, they react in presence of radiation to form the HCl, and this reaction has very high quantum yield. Such high quantum yield has been explained with the help of chain mechanism. So what is this chain mechanism? Say if you look at the primary process. In case of primary process, the chlorine molecule undergoes photolysis forming chlorine radical, correct? And in secondary process, these radicals propagate a chain process. You can see over here. So here is a chain propagation. So the large difference in the quantum yield of photosynthesis of HBr and HCl basically lies in the fact that the reaction 1 of this particular chain propagation is exothermic. And basically what I can say is this is exothermic in case of HCl. And hence the reaction proceeds rapidly in forward direction and increases the quantum yield. So this particular reaction is actually governed by this particular reaction, and therefore the overall rate of reaction, since it is exothermic reaction, it is self-driven, and therefore your quantum yield is so high. So one can understand from these mechanisms the interesting parts of the photochemical reactions, photobiological reactions, which are occurring in nature as well. So photochemistry that way is a boon, and we can understand lot many other examples. Right now in environmental chemistry or environmental science as a whole, photochemistry is playing a very important role uh, in predicting many of the phenomena and understanding many of the phenomena in nature. So friends, this is the end of this particular lecture, and this is actually the end of this particular paper, wherein we have started with the quantum chemistry, then we have started with the spectroscopy, and then now photochemistry. So all the parts we have tried to cover in this particular series of lectures, and we are now ending with this lecture with this paper. Thank you friends.